Demo.
That's cool. What'd you think?
I think the game looks amazing. I haven't spent a whole lot of time with that title yet, but I know I'll be bad at it.
Ray tracing is spectacular technology.
It is. It is. It's the subject of the topic that we're going to cover today.
Deep dive.
In the ray tracing technology deep dive. Thanks for joining us, Tom.
I'm very excited to be here. I can say that again on the level of difficulty, this is going to be a little bit more technical.
Okay. But I'm wearing my ray tracing.
I love it.
Shirt.
That is
not
the
really
Death
ray
Star.
tracing, but
Death Star.
It's dark side of the That's No Moon.
I love it.
Come on, it's good.
I love
It's
it.
good.
I love it.
All right, so we've talked about XESS.
Yes.
That was an earlier deep dive that we went into.
Yes.
Now we're going to do ray tracing.
Yes.
All on Intel Arc graphics.
Absolutely.
Let's start talking about it.
Okay. Well, we got to have a few slides about what is ray tracing, right?
Of course.
So I'm going to go ahead and try to talk through what's happening here. So this is where we all know and are comfortable. This is rasterization. And in rasterization, we're basically taking a three-dimensional model and we're projecting that to what's called screen space. And then we're effectively colorizing that with shaders. It's basically a giant simplification of how you would light a scene, but it's the way modern 3Ds work today. Now, ray tracing is very different. Some people call things ray tracing. It's really an algorithm called path tracing. Now, this algorithm is taking from the camera's perspective and imagining rays of light that are coming or projected out of the camera going through this grid of pixels, and then try to calculate what location would it intersect, what triangle would that ray hit, and then based on the color of that triangle, you can kind of calculate what the pixel color should be.
Got it. And this is interesting in that this is going kind of
backwards
reverse of how the real world works,
Exactly.
is we're path tracing into light sources as opposed to from.
Exactly.
Yeah.
So normally light hits things and it bounces and eventually it hits your eye or your camera.
Yeah.
In this case, to simplify things, we're projecting forward from the camera.
Got it.
Yeah. So that is ray tracing, or what some people call path tracing. Now the next step is kind of interesting. It's a combo, and we call it a hybrid rendering. Now in this case, you start by rasterizing the scene, which generates sort of a base image. But that base image doesn't have everything. It may not have good reflections. It may not have good shadows. So then you, in a parallel render, actually generate additional data and you fuse it together. So that's called hybrid rendering. Okay. Now if you look at all three of these together, where we start with, say, rasterization, and then to ray tracing and hybrid rendering, they're all just different ways of doing the same thing, which is trying to draw those game frames.
And I assume these three have different pros and cons across why you would do one or the other.
Absolutely. Like, for example, rasterization is just stupid quick, right? It is really, really fast. Ray tracing is very difficult. If you wanted to draw an entire scene doing nothing but ray tracing, it would be pretty slow, right? Because you've got to get lots of different samples of light to color just one pixel.
Okay.
And this hybrid rendering is something that's sort of emerged in the middle. There's parts of the scene that I can get a really good job done with rasterization, but these other things like reflections and shadows and maybe even ambient occlusion, you really do want to get more accurate.
I think we have a view of what that looks like.
Yeah, let's take a peek.
Combining rasterization and ray tracing.
Yeah, on this picture, what we're saying on the top is like rasterization, right? You're taking geometry and shader programs and you're rendering normal images. Yep. On the bottom is ray tracing. So it's at the same time as raster, it's doing its own, it's searching and it's generating its own light-based image. In this case, on the top, we do everything except this window looks kind of flat, right? You can see down here, it's kind of not a great looking window. But then on the right-hand side, we actually calculate a reflection. So the ray tracing unit sends a ray into this area, and it looks at what geometry did I hit inside that scene and calculates the color because it's bouncing off of the reflective surface. And if you look what's happening, they're being fused together post. It's really amazing, yeah. And the question is, how do you do that ray tracing image? It's another one of those moments that's going to be rocket science. Because if your first step might be to say, I have a ray, I have a bunch of geometry. All I have to do is figure out which triangle does that ray hit, And whatever color that triangle is, that's my base, and I'll take light and I'll figure out what light hits that triangle. That's what ray tracing is really doing, but it's horribly slow. So some smart people have figured out the right way to do this is called bounding volume hierarchies. And what you're going to do is you're going to draw boxes around geometry dynamically so that you search through the boxes to try to find the target triangle. Rather than searching all triangles, you search a small collection of triangles at the end of these boxes.
Going down a data tree of
Going down it's exactly a data tree. Okay, so I have an illustration of what that might look like. So this poor bunny is basically getting targeted by a ray. And what's happening is the ray is traversing this hierarchy incrementally, right? We start with the highest box that includes all of the bunny, and then the basic decision is, okay, there's lots of boxes at this next layer. This green box that I highlighted is the one that the ray actually intersects. So now tell me about the boxes inside that, and it finds a bunch of boxes, then it says, hey, find the next layer, find a bunch of boxes, and it gets smaller and smaller and smaller until it finally gets to a leaf. And at the leaf, it finds, hey, there's a bunch of triangles.
Leaf of the
data
tree
of the BBH,
in this case,
right?
The geometry of the bunny.
Exactly. So think of it as the bounded volume hierarchy is boxes, and at the end it says, hey, there's a bunch of geometry that's contained inside of this smallest box. Go look at these triangles to see if the ray hits.
Okay.
Okay, so it's a pretty interesting thing. So let's take one more shot at the bunny, and let's traverse the hierarchy one more time. And you can see this one's coming in. It kind of wings him a little bit, getting deeper into the tree, eventually lands in basically the back of his bunny. That little triangle right here is discovered, and went through like 4 or 5 different boxes to find that triangle. Okay, the cool part is, this you could almost write down a program and you could do this in a shader. It would just be pretty slow running this in a shader, and that's what we're going to talk about next. Okay, so the real question is, what's next? After you do a BVH, you might want to say, what's the work look like? Can we just do this in software, or do we actually need hardware?
Right.
So on the top, this is actually showing you all the compute that would be required to do this in software on a shader. This is a GPU accelerated BVH traversal. It's a typical ray tracing.
Even when done on a GPU, this is without a ray tracing acceleration.
This is just a compute shader, and it's showing you the floating point on the bottom and the integer instructions on the top. And it's basically doing that table walk through the BVH, and it's doing the shading at the end. Now, in our design, with our accelerated structure, all the while our hardware is active, the XE cores are still doing some floating point, but you can see using the accelerated structures, it's just much, much, much faster.
Good.
So the question is, what are these acceleration hardware pieces? How does that all come together? Well, let's go back to our architecture. We've already talked about this a few times. XE cores are the fundamental compute unit. They've got a vector compute called the vector unit, and they've got a matrix compute called the matrix engine, and all of that is just how you do normal rasterization. There's a bunch of graphics fixed function down there that completes the feature set that you need to do for rastering. So things like sampling your textures, a little bit of geometry coloring, rasterization. This is how graphics work today. You've got a lot of compute, and then you've got some fixed function that's shared across the XE cores.
And this fixed function has been developed, again, over those decades of how do I make rasterization
faster,
to fake all these other effects and lighting.
Absolutely. And it's very complicated because you're doing like depth and you're reading textures, and it's complicated stuff. And over the years, this is the collection of hardware that the industry has figured out is necessary to run well. Okay, the same thing is happening with ray tracing. So the way to think about it is, our ray tracing is kind of affiliated with XE cores because there's cooperative computing happening at the same time. You need XE cores to kind of initiate rays, and you need XE cores to shade rays. It's a very complicated dance, if you will. So we associate our ray tracing hardware with each XE core. Okay, so the 2 things you need are you need box intersection logic. Remember, we're going through this BVH structure looking at box intersections. And you also need triangle intersection logic. Because if you remember, when you get down to that leaf, the last thing you do is go and you tell me all the triangles. So those are kind of like basic functions, and I'd say that some people just do these things. And these can lead to very high peak rates of, like, if I have 1 billion places to do box intersection, I get 1 billion box intersections. But you need more than that to get a high performance ray tracing solution. And so that's what we did. We're out there doing our stuff. And now, instead of just doing sort of triangle and box intersections, we've created what's called a traversal pipeline. And I'm going to have to talk a little bit more about this.
A little bit, yes.
Yeah, because it's much more complicated. It's much more optimized for throughput rather than peak rates. And not just that, we have 2 of these traversal pipelines per XE core.
Okay.
Yeah, and lastly, we have what's called a BVH cache, which is a set of dedicated memory that stores partial results and partial, kind of parts of that BVH table that we talked about.
Okay.
All right, so there's lots of logic here. There's lots of stuff happening, and I'm going to show you how it works in just a minute. Let me go ahead and give you a couple of peak rates. So if you think about it, we do 12 box intersections per cycle, and we do 1 triangle intersection per cycle per core. Right. Okay. So depending on your clock rate,
do the math.
Do the math.
If you want your frequency, you can get to the peak box intersections per GPU
and triangle intersections. Yeah. And I just didn't put it on here because we don't really want to talk about our final clocks and our how many cores and all this stuff. That'll come later. But think about it for the ray traversal pipeline acceleration peak numbers. There you go.
Okay.
All right. So the question is, how does it work? Well, all of that extra stuff, the caching and the multiple RTUs and the full asynchronous pipeline, all that stuff delivers real performance. This is showing you effectively the 3D Mark ray tracing feature test. And you can see that we're at 1.29 versus 0.8 or 0.86 for NVIDIA's 3060, and these are gigasamples per second.
Okay, so this isn't a frame rate, this isn't a relative performance comparison. These are 1.29 gigasamples per second.
Exactly. Gigasamples is kind of like giga-rays per second, but each sample can generate multiple rays, so it gets kind of complicated.
Okay.
Yeah, so what we're basically looking at
impressive performance results.
A pretty high number relative to 3060.
Yeah. Okay.
Now, the second question is, okay, is that all you need? And it turns out there's one more chunk of secret sauce.
No, still not enough?
There's more that you need, and this is going to be a little bit more complicated. It's called the thread sorting unit.
All right.
Okay, any guesses?
Probably sorts threads.
Sorts threads, exactly.
Yeah.
But what threads? This is where things are a little bit funky. So the problem is when you're doing ray casting or ray tracing, you're basically searching the BVH hierarchy and you're landing on a triangle. Now, each of those triangles has different shaders associated with it. It might be different objects, it might be different materials, and all of those shaders are just sort of suddenly discovered. But you have this massive pile of work in front of you. You need to shade all of these triangles to figure out what to do next. Okay. Sometimes you're going to I'm done casting, please shade a color. Sometimes it's going to be, I need to cast another ray, or sometimes it's, I need to terminate this ray. So you've got a pile of work in front of you, and if you just sent that off to the XE cores, some would go quick and some would go short, and that's what I'm showing here with this sort of coherency. Lanes are happening inside of each XE core, and if you have things only going a little bit, then all of this time on that XE core is basically wasted, right? You want all of your XE cores to be running fully saturated all the time. And to fix this, what you need to do is put the things that are long together. Okay. If you put the threads that are long together and the ones that are short together, then you can fully utilize your XE cores. Okay. So the way that looks is something like this, right? You take all this jumbled independent ray data, you go through the sorting of like what type of materials is it, and then you can actually execute in the XE cores.
So the different colors here represent similarities of the shader that the ray is resulting, or whatever the work is at the end of that.
You're exactly right. We searched through all the BVH, we found the triangles, we got a whole list of triangles that we need to shade, basically figure out what to do with next. And how do we get that work done? Well, we need to sort them to put those into the same buckets so that they will all execute with roughly the same amount of time.
Sorting unit improves the efficiency of the throughput of everything.
Yeah, it improves everything.
Removes the bubbles from the pipeline and makes us
You are exactly right.
faster.
Okay, that wasn't too bad, right?
No,
not bad. We're sorting.
Colored boxes I can understand.
Colored boxes. I think we can all get it, right? We're sorting because it improves efficiency, and efficiency is throughput.
Okay.
All right. Let's tie all this together. Asynchronous ray tracing. On the front end, we have ray generation, where you're sort of creating the structure of how many rays do I have. It's got the origin, the direction, a bunch of metadata, and that's like your work set. Then that gets issued and run on our ray tracing unit.
Okay.
The ray tracing unit's doing all that BVH traversal, it's finding hits, it's eventually getting down to leaves for all of the rays, and it calculates a bunch of hits, a bunch of different shaders that need to be executed per pixel. Okay, now the shaders are all going to be different types, and that runs into our thread sorting unit that puts them into sort of coherent groups.
Organizes.
And the coherent groups are sent back to the XE unit, the XE core, where they're shaded, and then the final result either issues additional rays, or it retires rays, or it colors pixels.
Okay.
Pretty exciting.
Yeah.
That is an advanced ray tracing engine.
I love it.
All right, so what does it do? Well, at the end of the day, we've got this demo that I want everybody to see. It's called the Intel Spheres demo. And it has alpha cutouts, which allows rays to traverse through these spheres. And in this result, you'll see we run 69.5 frames per second. That's the A770 again. And that happens when we have just one shader. So when you don't need to do any kind of sorting, when it's all the same material, we get 69.5 frames per second. Now, if you have 128 different types, which maybe one's shiny, one's bumpy, one's transparent, maybe one is sort of like diffracting, all of that kind of difference is different shaders. And those shaders, when you have 128, our performance goes down to 52.8 frames per second. And that's bad, but it's not that bad, right? It's 10 frames per second out of 60. And this is as good as it is because of our thread sorting unit. If you compare that to comp, they're starting out at 33.9 and they go down to 21.6.
So it's a much larger relative performance decrease because of that variability of the kind of the I won't say randomness, but results of the ray tracing.
And more different materials will increase this difficulty, right?
Right.
So by adding this thread sorting unit, what we're really doing is we're enabling the ecosystem, we're enabling ISV developers to be more free with materials.
Okay.
Pretty neat. So we have a powerful ray tracing architecture. I think the engineers and the architects should all just, hey, whoa. Good stuff, right? We have one TSU per XE core, and it does high performance asynchronous ray tracing. We got one RTU, which is the ray tracing unit per XE core, two ray traversal pipelines per XE core, 12 intersections per clock, 12 box intersections per clock, one triangle, and we have a dedicated BVH cache. That's some stuff.
So that is the architecture about why our ray tracing implementation is good.
Yes, and we support DXR 1.0, 1.1, and Vulkan RT. So all of the major APIs are accelerated on this RT engine.
Okay, that's good.
It is good.
Great to understand the technology. Great to see the hardware and all the great engineers that have put all this stuff together. But
oh, you want to see?
I'd like to see it actually in a game.
Okay, well, why don't we go take a look at Ghostwire Tokyo?
Let's do that.
And we'll see what we've got. Okay, so we're in Ghostwire Tokyo, and it's a futuristic scene. It's got ray tracing enabled on this side, on my machine, Ryan, ray tracing off on your side. But right away, I mean, just sitting here, you can see my scene has beautiful reflections, great detail, but yours has reflections too, right? But right away you're like, okay, well, how's that possible? Ray tracing's not enabled. Well, the truth is you're seeing a technique called screen space reflections, and maybe we'll learn a little bit about where is that good and where is there a limit. So let's go ahead and go forward, and then we're going to take a right, and we're going to go down this little, past the umbrella, past the stairway, and we're coming past this. Look at all my little reflections are looking really good. And then we're going to see that red umbrella, and we're going to come in front of these 3 green lights. Okay? Now we're approximately the same spot. You can see the umbrella. Back up a little bit. Now, the reason I'm here is because in my lights I can see some text. I can see some more detail in the shadows. I can see this reflecting. In yours, I just see sort of green smudges.
Yep.
Right, and that's all because they're doing an approximate reflection. Now, another cool thing about reflections is they're supposed to be persistent. So in my case, if I rotate downward and move the green things off the screen, my reflections stay there. Your reflections disappear, right? Yes. So what's going on with that, right? It's this whole idea of screen space reflections, where if you don't have the object drawn in a pixel on the screen, you can't project it. You can't. So it's almost like a baby where there's no persistence of objects, right? There's no persistence of light in this title when it's screen space reflection. Okay. So now look to the right, and we're going to walk down a little bit. And kind of, again, look at my reflection here on the ground. You see how mine has, there's like a building off in the distance there somewhere. And if you maybe back up a little bit, you'll see, hey, you don't have a building really. And then if you rotate down, you'll see how that kind of changes. So look at your reflection as you rotate up, and then something weird's happening, right? What is that? So again, there's a moment when there's a screen space reflection, but then there's a moment when there's nothing. And so when there's nothing, the game is going to draw sort of an interesting background texture on reflective surfaces. So all of those artifacts are the difference between ray tracing and traditional raster. So let's go over here and take a look at one more thing. Take a right, and we're going to come over and look at this LED thing. So as we're walking, you can see I'm getting very crisp. This is pixelated because it's actually looking at individual LEDs over here on the wall. So if we back up, I'm backing up, you're backing up, and we're going to take a look at my cool reflections. And you can also see over here in the window, mine's generating real ray traced reflections on the floor. Yours is looking a little bit more like a blur. And it's the same idea. If you rotate down, you're not going to see your colors as you are dealing with it, right? They kind of disappear and they turn into that white thing, right? It's just a little bit jarring to have your reflections disappear.
Got it.
Okay, so that is the difference between real ray traced quality, and on Ryan's machine, it's using traditional rasterization screen space reflection.
Great demo. I didn't have to die in this demo.
You didn't die. I love
purposes of entertainment, so I appreciate it.
People always see reflections in rastered games, right?
Yeah.
And this is the first time I think we've ever explained. Well, it's called a screen space reflection,
right?
And it's a trick. It's not a trick. It's a technique to try and get something to look like it's reflected when there's really no reflection happening, right? So let's talk about more than Ghostwire, okay?
More than the one title.
More than the one title, and you know how we're doing right now. We're giving full disclosure. So here we are. This is our ray trace enabled game performance, and we're showing the Arc A-770, and you can see we're stacking up our performance. Again, this is done apples to apples as much as possible. The system configurations are all in backup, driver numbers, all the rest of that, and you can see our ray trace performance versus NVIDIA is, kind of some we win, most we win really, but it's, some we lose.
Sure.
And what I really like is this is another example where our engineering team is just cranking, right? We say, what's going on with Ghostwire Tokyo? And they're like, I'll be right back. And so now we have a brand new beta driver on Ghostwire Tokyo that improved performance by 25%.
That's a pretty good amount.
Yeah, and it's just an example of, we've mentioned a couple days, a couple times, it's early days for us, and things are going to continue to get better. Yeah. This is one great example.
Very good.
All right, but I like to normalize, right? Normalizing, normalizing removes all the ambiguity, and all of a sudden you can see, okay, there's a couple that were down, but most of them were up on. So our ray traced performance versus 3060, I think it's pretty compelling.
That's very impressive. Yeah.
Now let's take a look at 1440 games, and in this case, the performance on our Arc 770 at 1440 with real high ray tracing is, it's going to be hard to enjoy this 25 frames per second, 34 frames per second, but this is where XeSS really comes in, right? XeSS running balanced, 25 goes to 44, and on performance, 25 goes to 52, 34 goes to 68. It's just a pretty awesome combo.
Yeah, I mean, even something like Hitman 3 going from just over 30 to well over 60, near 70.
Yeah, magic number.
By turning that on.
We talked about that.
And we've talked about XeSS. We know how it works. We know what image quality capabilities it provides too.
And it's key that XeSS seems to be very well matched to ray tracing, right?
It is. It's a great ability to continue to improve image quality without sacrificing your frame rates and performance that enthusiasts want.
Yep, I just showed you again the impact of the new beta driver. We're now up to 30 and 64, so things are going to constantly be sort of tweaking. Pretty excited. Normalizing, you can see our speed up because of XeSS is somewhere around 2. Again, these numbers are going to be bigger at the more frame rate challenged end of the thing and less at the high end. We've already talked about this in the XeSS video, but it's great results. Okay. So we have to one more thing. We're very happy to say that Gotham Knights is going to be launching on October 21st with ray tracing. Our dev tech and dev rel teams have been busily integrating there.
I'm looking forward to this title. And this is just key art, but they got a lot of reflections on the
There's a lot of reflections. You can see some soft shadows. I'm pretty excited about it. It's going to be great. So let's wrap it up.
Okay. I mean, what's the takeaway for me for this from ray tracing is that we have built a very competitive leadership, maybe I might say, ray tracing capability in the Arc GPUs.
Yeah, I think so. I think so.
And gamers and consumers can be able to take advantage of that in combination with other technologies like XeSS.
There's absolutely no question. Our ray tracing hardware is, definitely at the front end. I mean, ray tracing is still relatively new technology.
Sure.
So not just us, NVIDIA, AMD, everybody's investing into ray tracing because it's giving good results, right? Physically, much more believable worlds. And I think that's going to become, a continued trend where we're always struggling for realism. And right now, ray tracing is a pretty compelling way to do it.
How far are we from having fully ray traced game titles? Right? We moved away from the rasterization side and the pinnacle of
this is one of those like when you start talking about photorealistic gameplay.
Yeah.
And I honestly don't think in the short term there's a time when render based on rasterization is not like a good first step, and then you add effects. But the truth is, movies don't do it like that. You know, movies do fully ray traced scenes, but they're running, you know, weeks.
Definitely not real time.
Yeah, but that's not. It's not like impossible to imagine today. But it's just not anytime soon. And furthermore, it's not ever clear that in a power constrained world, you'd really want to spend all your power on ray tracing. There's all these kind of interesting combos that I think are going to come and get much better before we shift to, say, a path traced game environment.
Okay.
Yeah.
Super interesting.
Yeah.
Thanks, Tom, for walking us through ray tracing technology, education before you get to the data and the gameplay. Thank everybody for watching. Thank you, everybody, for watching here. Arc.intel.com. Go there, find all of our content, all the details about technology and features and capabilities and performance of the Intel Arc graphics products as we get ready for release.
It's going to be cool.
It's going to be fun. Thanks, everybody.